In previous video, I derived Euler-Lagrange equation, and in this video, I am using this approach. I am using this Lagrangian approach for solving two classic problems in physics. That is the Atwood machine and the simple pendulum. So now these are the steps which are involved in solving the problems using this Lagrangian approach. The first is the identify constraints in the system. We should first identify the what are the constraints in the system. Either they are holonomic or non-holonomic. Use these constraints to reduce degrees of freedom. So if these constraints are holonomic, then we can reduce the degree of freedom, and as a result I can get the generalized coordinate. Next, we have to find this Lagrangian function L, which for most of cases is difference between kinetic energy and potential energy. But there are some cases in which this is not true. And the final step is to solve this Euler-Lagrange equation which we already derived. So we are going to solve this. Okay, so the first problem is the Atwood machine. It consists of an frictionless pulley and two masses M1 and M2, which are connected by a massless and inextensible string which is passing through this pulley. So we can see that if M1 is greater than M2, so the M1 will move downward and M2 will move upward. So there is only 1 degree of freedom. So let's say the coordinate of this M1 is x1 and M2 is x2. So I can write the kinetic energies for these two objects, that is half m1 x1 dot square plus half m2 x dot x2 dot square. So I can also write the potential energy as minus m1 gx1 minus m2 gx2. Here I have chosen the top of this pulley as my reference. That's why I am taking this negative as gravitational energies, since you know that gravitational potential energy is taken as mgh. So if I can now I know this T and V, so I can find this Lagrangian, which is L is equal to T minus V. So the first two terms in this expression are kinetic energies and the second two terms are the potential energies. But now we have here a constraint, and this constraint is that x1 plus x2 is equal to L, means that the length of the string is constant. So if it is so, then I can express one coordinate in term of other. So I can express this x2 in term of x1, or I can express x1 in term of x2. So both ways are true. So if it happens to be so I can express x2 is equal to L minus x1. So x2 dot will be minus x1 dot. So I can put these values in the above equation, in this equation. So I will get the first term is as it is, and the second term I will put x1 dot square, because if we are dealing with the square, so negative sign does not matter. So the next is in third term is same, and the fourth and fifth terms get changed. So in the fourth term we have m2gl minus m2gx1. Simply we have put these values in the above equation. Okay, now we have obtained the Lagrangian for this system, so now I can differentiate it with x1 and x1 dot, and then finally I can take time derivative to find the equation of motion. Please note that there is only one independent variable, which is x1. So our Lagrangian is given by this equation. Now this is our Lagrangian function. So we have obtained this function, so all we have to do is to differentiate it partially once with respect to x1 and then with respect to x1 dot, because x1 is the only independent variable. It is the generalized coordinate. So the first, second and fourth term do not contain this x1, so their derivatives will be 0. So the 0 plus 0, and from this term I will have m1g, and the for fourth term will be 0, and from this term, fifth term, I will get minus m2g. So this can be put as my m1 minus m2 into g. So next we have to take its derivative with respect to x1 dot. So I will get this expression, that is m1 x1 dot plus m2 x1 dot, which can be put as m1 plus m2 x1 dot. So this is the Euler-Lagrange equation, so I need to put here values. So d by dt as it is. So now next I put this value above value in this equation, which is m1 plus m2 x1 dot, and minus, and the value of partial L by partial x1, and this is put equal to 0. So the only variable is x1, so this will get double differentiated, so I get m1 plus m2 into x1 double dot, which is equal to m1 minus m2 into g. So finally I can get this equation, and this is the difference of masses over sum of masses multiplied by g. So this is the equation of motion. And okay, the second problem is the another classic problem in physics, which is the simple pendulum. So we have a small mass m which is connected with the help of an inextensible string to a fixed support, and at any instant of time the angular displacement is given. So now I need to write the Lagragian for this system. So the kinetic energy of this system is given by this relation, that is half m L square theta dot square. L square theta dot square is the square of the tangential velocity, because from circular motion we know that the tangential velocity is equal to r into omega. Omega is angular velocity, so in this case this angular velocity is theta dot. So this half ml square theta dot square is the kinetic energy of this simple pendulum. Okay, so the next term is potential energy. So let's assume when theta is equal to 0, that is when our particle is in the vertical direction, then at that moment the potential energy is 0. So when I displace this particle through a small angle theta, then this particle is displaced by L minus L cos theta along the vertical direction, because total is L, and at any moment this vertical component will be L cos theta, so the difference is L minus L cos theta. So thus I can write this Lagrangian, that is L is equal to half ml square theta dot square minus mg L minus L cos theta. So this can also be written as, I can take L common, so I can write this way. So this is our equation. So all we have to do is to differentiate once with respect to theta and once with respect to theta dot. So when I differentiate this with respect to theta, so the first term does not contain this theta, so its partial derivative will be 0, and from the second term I will have minus mgl sine theta. And when I differentiate this with respect to theta dot, so the only first term has this theta dot, so this will become ml square theta dot. Next I need to put these values into the Euler-Lagrange equation. So when I put this, so this will become minus mgl sine theta is equal to ml square theta dot. So after cancellation of m and 1l, we will get theta double dot, which is equal to minus gl by sine theta. So now this is the standard equation of simple pendulum. However, if this theta is very small, so I can expand the sine theta in terms of series. So from there I can get minus g by l into theta, and that in that case this motion will be simple harmonic motion, but it is only for very small theta.